Alright, welcome back to this week's problem of the week, a rational sequence 2. Alright, a sequence of positive rational numbers is defined as follows. An infinite full binary tree labeled by positive rational numbers is defined by a label root of 1, 1, the left child of PQ, which is P over P plus Q, and the right child of label PQ, which is PQ over Q. The top of the tree is shown in the following figure. So as you can see, right, the left child is the basically you sum the numerator and the denominator. That becomes the new denominator. And the right child is the opposite, and it kind of goes down. All right, the sequence defined by doing a level order breadth first traversal of the tree indicated by the light dashed line. Right, so you basically go like this around and you hit all the points. So that f of 1 is equal to 1, 1, f of 2 is equal to 2, 2. They're basically just describing how they're counting the nodes, and they count them left to right from row to row. Write a program which finds the value of n for which fn is pq for inputs p and q. So it basically wants you to find what value the a given fraction is. And then they give you a couple of cases, and you have to return it. Okay, I'll go over the code now. Let me try reloading my Replit. Okay, so the code is pretty hefty because I kind of approached it from a brute force perspective. There may have been a mathematical way to do it in hindsight, just looking at the traversal of a binary tree. I'll just go over how I brute forced it. And really the time complexity is not that high, so it is still a fairly standard solution. All right, so as usual, you take the input and you run that many cases. I do some splitting, and I run this function called root. Now basically what root does is it returns me the movement pattern and the binary tree level. So the movement pattern is in the array movement, and then the binary tree level is another array. All right, I'll run through this. Count, that's basically saying how many levels you're going down in the tree. I declare some of this stuff. I do a little bit of data parsing, and then I cast it. Here is basically I'm working backwards. So if you remember, they give you the fraction here. So I'm working my way backwards while it's not 1, 1 basically. I add 1 to the count, so this adds 1 to whatever layer of the tree you're on. And then here you either make a right move or a left move, right? Because the binary tree, you either go left or right. Here I'm saying if the numerator is greater than the denominator, so as you can see, if the numerator is greater than the denominator, you're always moving right. So that's how you know you've done a right move. And then I do the numerator minus the denominator, because basically what I'm doing is I'm reversing this operation by subtracting it depending on what the movement is. I basically do that a bunch of times until I work my way back up the binary tree to 1, 1. And then I reverse it. So I reverse the movement tree, so now I can work my way down. I remove the last element of summed, and then I return everything. All right, so we come back to here. I have a bit of debugging just to see what I return, so I make sure it works. And then I run this other function called find, and this basically finds the placement. So obviously if the count is equal to 0, this means that it's on the first level because you have 1, 1, in which case you just return 1. Next, I'm creating a simulated row with the total number of nodes in the tree's row between 1 and whatever the complexity is. And I get this by basically saying the node is going to be somewhere on this level between node 1 and 2 to the power of however many levels it is. Right, so like here, let's say I'm on level 2, the node is going to be between 1 and 2. This is one level down, so I'd be between 1 and 2 to the power of 1. Moving to level 2, this would be between 1 and 2 to the power of 2. So basically I'm just creating the bounds for the row. Here I'm running a binary search which uses the left and right decisions to narrow down the row because if you remember, here you're making a binary decision on whether you go left or right. So that's what I'm doing here, and I'm basically cutting off half the row each time depending on whether it's left or right. If you remember, I have the movement array here which tells me the order that the person made the left or right choices. And then this is just pretty standard binary search stuff. I'm just splitting the array in half basically, and then I do a bit of debugging. If you're interested, you can go search up binary search pattern and then read about it, but I won't go over it too much here. And then here we use the last path decision to determine what the final placement of the object is in the row. So basically what I'm saying is on your last movement, you either have one or the other. So I take this last one and I just return you a value. So it's, if it's left, you're getting the left node. If it's right, you're getting the right node. And then it returns out here, and I get the placement here. So I'll run the sample input for you guys. And as you can see, it runs pretty quick, even though this code is rather hefty, because you really only have one iteration. You don't have any nesting, so as far as the runtime goes, it's pretty linear. And then as you can see, it's working out, and it kind of just grinds through the large test cases. So pretty long problem of the week video today, but this was an interesting problem. I'd encourage you guys to make sure you really understand all the stuff that's going on. All right, have a nice weekend.